Section 4.4 Tangent Planes and Linear Approximations. Tangent planes. In three-dimensional space, many lines can be tangent to a given point. If these lines lie in the same plane, they determine a tangent plane at a point. A tangent plane at a rectangular point containing all the lines tangent to that point. So for this problem, it's important to recall what is a derivative and what does it help us find. So if you think back to maybe like your Calc 1 class, you would find the derivative, and given a point, it would help you find the slope, and then you could create a line, right? So extend that same idea to this multivariable course, but instead of a slope and a line, we're finding the equation of a plane. Definition of a tangent plane. Let P0 equal x naught, y naught, and z naught be a point on surface S. And let's see but any curve passing through P naught and lying entirely in S. If the tangent lines to all curves C at P naught lie in the same plane, then the plane is called the tangent plane to S at P naught. So here we see some specific point may vary from your problem, but at this point we can create a tangent plane, which is this part right here. This sheet right here is our tangent plane at that point. And there we see we have our curve C. Next definition. Let S be a surface defined by a differentiable function z equals f of x comma y, and let P naught equal z naught comma y naught be a point on the domain of f. Then the equation of the tangent plane to S at P naught is given by z is equal to f of x naught y naught plus f of x of x naught comma y naught times x minus x naught plus f of y x naught comma y naught times x minus y naught. When I think of this equation, I think of your point slope formula. So I think of this, when I see this, I think of this as your multivariable point slope formula. Now, since we're going to be given a specific point where you see these sub-zero values, those are our points given. So we're going to find the derivative of x and plug in those points. I think it's not right to say it. Right, so why don't we say, and then plug in those points. And then here we'll find the partial derivative of f in terms of y, and then plug in those points. And here it's just our function f, and you plug in those points. Okay, let's go ahead and do an example so you can make more sense of this. Find the equation of a tangent plane to the surface defined by the function f of x comma y equals 2x squared minus 3xy plus 8y squared plus 2x minus 4y plus 4 at point 2 comma negative 1. Okay, to begin, let's find the derivative of our function in terms of x and y. So first, let's find f of x comma y, and let's find f of y, x comma y. Okay, so we have our function, and I first want to find the derivative in terms of x. So I have 2x squared, which gives me 4x, times 3xy. Y is a constant, but the derivative of x is 1. So I have plus or minus 3y plus 2. The derivative of 2x is 2. The derivative of 8y squared is 0, so we can disregard it. The derivative of negative 4y is 0. The derivative of 4 is 0. Okay, so we have our first derivative in terms of x. Now let's find derivative in terms of y. So we look at our function and I want to find derivative in terms of y. For our first term, it's x, so that's 0. Second term, the derivative of y is 1, so we have minus 3x. For our third term, we have y. 8y squared is 16y. Derivative of 2x is 0. The derivative of negative 4y is negative 4. Derivative of 4 is 0. Okay, so our derivatives are 4x. For x is 4x minus 3y plus 2. And for y, we have negative 3x plus 16y minus 4. Okay, now we want to plug in those points of each derivative. So I want to find f of x, and then our specific point we're given is 2 and negative 1. So 2 comma negative 1. So let's plug in a 2 for x and a y, negative 1 for y. So that we have 4 times 2 minus 3 times negative 1 plus 2. Our answer is 13. That's our first important point. Next, I'll do the same thing with y. Plug in that x naught, y naught. So that we have negative 3 times 2 plus 16 times negative 1 minus 4 equals 36. I'm sorry, negative 26. That's going to be part of our equation too. Next, we want to find our function at that point. So f of x naught comma y naught, or we should say 2 comma negative 1. That will give us 2 times 2 squared minus 3 times 2 times negative 1 plus 8 times negative 1 squared plus 2 times 2 minus 4 times negative 1 plus 4. That gives us 34. So these are all the numbers we're going to be using. Now we're going to recall our formula that we have right above. We have z is equal to f of x naught comma y naught plus f of x naught comma y naught times x minus x naught plus f of y x naught comma y naught times y minus y naught. All right, well, we have these pieces. They're actual numbers. They have a value. Let's go ahead and plug those in. So that we have f of x naught comma y naught is 34. So I have 34 plus f of x, our derivative. We have 13, and then x minus our x naught is that 2, plus, and then we have minus 26 times x, y minus negative 1. Okay, let's clean that up. So we have 34 plus 13x minus 26 minus 26y minus 26. Combine like terms, our equation of our plane at that point, tangent to that point, is 13x minus 26y minus 18. And there we have it. So our values that we came up with came from our derivative at that point of x, our derivative in terms of y at that point, and the actual point of our function. It's a lot of steps, but the steps itself are not so bad. Okay, let's do another example. So we can work with some trig functions. Okay, so just as before, let's start off by finding the derivative of our function in terms of x and then in terms of y. So f of x, x comma y. So our x is only here, so we only have to take derivative there. Well, that entire sign. So we have to do chain rule. Derivative sign is cosine. So we have cosine of 2x, and the derivative of our argument inside our parentheses is 2 times 3y. Okay, our derivative of y in terms of our function in terms of y. Well, similar idea. I just want to keep my eye on the y. So that I have I still need to bring this down because it's a constant. So sine of 2x. There we go. Okay, now for y, I want to look at the y, and derivative of cosine is negative sine. So I have negative sine of 3y. Derivative of our argument is 3, and then that sine 2x is still there. Okay, so let's clean them up. So that I have 2 times 3y gives us 6y. So I have 6y cosine of 2x and then sine of 2x. F of y, x comma y, we have I did that first derivative incorrectly. Let me do it again. Derivative terms of x, we have that. So derivative of sine is cosine, so I have cosine of 2x. And then I take derivative of the inside is 2, and then I bring down my cosine 3y. There we go. So then I have 2 cosine 2x, cosine 3y. Okay, and for my other one, I have negative 3 sine of 3y, sine of 2x. Okay, let's go ahead and plug in those points. So f of x at this point pi over 3 and pi over 4 gives us 2 times cosine of 2 times x, which is pi over 3, and cosine of 3 times y. Y is pi over 4. So this gives us 2 times cosine at 2 pi over 3 is negative 1/2, and cosine at 3 pi over 4 is negative square root of 2 over 2. So that we get as an answer square root of 2 over 2. Okay, and for y, let's plug in those points of pi over 3 and pi over 4. Get negative 3 sine times 3, and where y is pi over 4. And then sine of 2 times x, which is pi over 3. So that we get negative 3 times square root of 3 over 2 and square root of 2 over 2, which gives us negative 3 square root of 6 over 4. Okay, and we also want to find the value of our function at that point. So f of pi over 3 and pi over 4. So we plug it in, we have sine of 2, and for x, we're going to plug in a pi over 3, and cosine of 3 times y, which is pi over 4. So we get sine of 2 pi over 3, and then cosine at 3 pi over 4. They evaluate to be square root of 3 over 4 times negative square root of 2 over 2. You get negative square root of 6 over 4. Okay, we're going to use these values into our function. So our formula z, or our equation of our plane z, is negative square root of 6 over 4 plus square root of 2 over 2 x minus pi over 3 minus 3 square root of 6 over 4 times y minus pi over 4. We distribute those values in, and we're left with z is equal to negative square root of 6 over 4 plus square root of 2 over 2x minus 2 pi over 6 minus 3 square root of 6 over 4y plus 3 square root of 6 pi over 16. And that's it. Linear approximation. Given a function z equals f of x comma y with continuous partial derivatives that exist at the point x naught comma y naught, the linear approximation of f at the point x naught comma y naught is given by the equation L of x comma y is equal to f of x naught comma y naught plus f of x naught comma y naught times x minus x naught plus f of y of x naught comma y naught times y minus y naught. Notice that this equation also represents a tangent plane to the surface defined by z at a point. The idea behind using a linear approximation is that there is a point x naught comma y naught at which the precise value of f of x, y is known for the values of x comma y reasonably close to x naught comma y naught. Furthermore, the plane that is used to find the linear approximation is also tangent to the plane to the surface of the point x naught comma y naught. So what we're saying here is we have a point that's really close to the point we want to work with. We can approximate and use a point really close. So this is our main point. But I can find a point that's sort of close to it. I guess you can kind of say it's in that neighborhood of it or close to it. And I can create a tangent plane to that very close point. Now, why would we do this? Well, I guess you can say that we could use it to find a point that's easier to work with. But more precisely is because what if at that point we're trying to differentiate and find the tangent plane? What if it's not a smooth continuous part of our function? What if it's some sort of some peak, for example, not a peak, but some part where it might be the continuity of the function might be something you're not too sure about. Well, you can always pick a point that's very close to the point you want to work with that you're not too sure about the continuity. So in this example, given the function of f of x comma y equals the square root of 41 minus 4x squared minus y squared, approximate f of 2.1 and 2.9 using 2 and 3 for x naught comma y naught. Okay, so it's just as before, but we're going to disregard this point and work with these points here. Okay, well, it's just as the steps before. So we want to begin by finding the derivative of our function in terms of x and then in terms of y. So if we want f of x, x comma y, we get, well, we have to perform chain rule. So we can think of this exponent as 1/2. So 1/2 of 41 minus 4x squared minus y squared, and then 1/2 minus 1 is negative 1/2. Then we take our derivative of what's inside, which in terms of x that's our only term that I can take derivative of. So I have negative 8x. And then we can clean it up. So I have a negative, going to have a fraction, the square root of 41 minus 4x squared minus y squared. In the numerator, I have 8 divided by 2, so I have 4x. Okay, now in terms of y, almost similar. So again, chain rules, so I have to bring down the 1/2. And then I have 41 minus 4x squared minus y squared, so negative 1/2, times our inside argument, but I only want y, so it'd be negative 2y. Let's clean it up. So I have negative, I have denominator of the square root of 41 minus 4x squared minus y squared. And 2 divided by 2 is 1, so I'm just left with y on the numerator. Okay, I want to evaluate at that derivative for the point. So I have f of x of 2, 3. I input this value, so I have negative 4 times my x is 2, square root of 41 minus 4 times x, which is 2 squared, minus y, 3 squared. We get negative 8 over 4. That's negative 2. Now for y, the derivative of y in terms of 2 and 3, we get negative, and our y is 3, and our denominator is the same. So I have 41 minus 4 times 2 squared minus 3 squared. So you get negative 3 over 4. Okay, now our point, let's evaluate our function at that point. So I have the square root of 41 minus 4 times 2 squared minus 3 squared. We get the square root of 16, which is just 1. Okay, let's go ahead and find our function or our equation of our plane. So it would be made up of 4, and then minus our x. Our x we got 2. So negative 2 times x minus our x point is 2. And then our y, we have negative 3 over 4, and y minus our y point was 3. Now we can clean it up. We distribute those values into our parentheses, and we're left with negative 2x minus 3 over 4y plus 41 over 4. Now, for the sake of not making this video too lengthy, I will not do the linear approximation or the tangent equation of that point using 2.1 and 2.9. But the error between these 2 points is very small. It's less than 1%. There is a 0.2% or 0.02% error. So this is pretty valid. It's pretty safe. All right, so that was 4.4 tangent planes and linear approximations. Your homework is problems 171, 173, 175, and 177. Thank you.